We are living today in a new era of data, and new machine learning and deep learning capabilities have enormous variety of applications that stretch into many sectors in the economy. And in finance sector, nasdaq has been playing a pivotal role in leveraging the cutting-edge technologies to maintain healthy financial market. I am Hyun-Soo Jung from nasdaq, and I'm going to talk about nasdaq Analytics Hub, which provides traders, fund managers, and financial institutions with finance and alternative data sets. So how many have you heard about alternative data set? And yeah, sure. Yeah, so let me talk about briefly what I did last weekend.
There we go.
So I woke up around 7 o'clock by alarm app. You can get sleep cycle data from the app. I usually start a day with Americano. So on my way to Starbucks, I can get geolocation data from my mobile device. At Starbucks, I bought Americano, and you can get payment transaction data, right? And sitting at the table, I check the current status of my patent application. Can get patent information, patent data from USPTO. And I also read some news article, and you can get sentiment data, news sentiment data by using NLP, right? And in the afternoon, I went to a shopping mall to buy some stuff. And at the parking lot of the shopping mall, we can get satellite image data, which could be a measure for the number of people visiting the mall or retail shop. And in the evening, I opened the box for box that I bought at the mall, and I really liked the quality of the product. So I decided to leave a positive, very positive product review in their website. And you can get the product review data by web scraping. And before I went to sleep, I was wondering how much data scientists earn on average in a year. So, yeah.
Helps you sleep better at night.
So I checked it out at glassdoor.com. And yeah, we can get job posting data by web scraping. So that's just for one day, right? But actually, I generated a bunch of data set. And if I want, I can collect all of them. And every data set I just mentioned is alternative data. So many alternative data sets are available out there, and the number of companies using the alternative data for investment is rapidly increasing because they see huge potential of the data for their investment strategy. But at the same time, the number of challenges in using them is rapidly increasing as well. So most of it is not easy to find the useful data from tons of different data sets. And most of them are quite incomplete, quite messy, unstructured. So you have to clean it, normalize it in order to, before you use it for further analysis. And also, if you want to use the alternative data set for investment, your data set should be linked to any kind of tradable instrument, such as ticker symbol. And if you want to use it for the investment, you need sizable history for backtest. Let's say you're very lucky and you find very useful data with a history of 10 years. And on top of that, your data set contains ticker symbol. But that's not enough, because ticker symbol information can be changed over time. For instance, if a company is acquired by another company, if a company filed for bankruptcy, or sometimes company just changes its name and ticker symbol information for some reason. In such cases, ticker information changes over time, and you have to deal with it properly. And that we call that process as symbology mapping, which is very tricky and complicated. As you noticed, there are so many challenges in using the alternative data set, but if you use NASDAQ Analytics Hub, you can overcome such challenges very easily. We find useful data from tons of different data sets. We clean them, we normalize it, and we evaluate the data set, we backtest it. We also do symbology mapping. And we not only evaluate the data set, but also make tremendous enhancement on the data. And you can get the data set from our FTP or API. And today we are going to focus on two parts: data evaluation and data enhancement. I'm going to cover the first part, and Dr. Hamilton will deep dive into data enhancement part. So when we do data evaluation, we are using couple of quality metrics. We figure out how many missing values are in the data, how good the quality of data set is in terms of investability and symbology, how many tickers the data can be covered, and how long the history of data goes back. And as I mentioned, we make tremendous enhancement on the data. We do feature engineering. We use graph search. And we also use reinforcement learning. But I know you're very curious about data enhancement, but please bear with me. Dr. Hamilton will deep dive into it very shortly. So we can think of NASDAQ Analytics as finding a needle in a haystack. So most of data sets are seemingly unusable, incomplete, quite messy, but just like untouched hayfield, but we find useful data from the tons of different data sets, and we clean them, we normalize it, and just like we mow and make haystacks. So once the data sets are ready for the further analysis, we derive the signal. We evaluate the data set by using a couple of metrics. So just like finding a needle in a haystack. And then you can just use the needle for your needs. So what is needle? So it can be, I would say it's platinum needle rather than gold or silver, because platinum is much more precious and rare and precious than gold or silver. So yeah, it could be a valuable information. It can be an alpha signal for trading, or valuable information can be used for portfolio construction or index creation or strategic planning or operations management. Let me show you how actual alternative data sets look like. You will see incomplete data set with many missing dates in time series. And your data set would contain a lot of outliers in the middle of nowhere. And part of your data set may contain nothing. And the ticker coverage of your data set is fluctuating over time. But you don't have to worry about this kind of incomplete, kind of messy data set because we clean them, we normalize it, so making kind of unusable data usable. And then we derive the signal from the data set, making usable data valuable. So I'm gonna show you how to evaluate the data. I'm gonna take two different data sets for examples: patent data and product review data. So this is patent data. Patent data gives you an insight over the strategy focus area of a company. So this stacked bar plot is for one of the major tech firms. And as you can see, since 2014, this company has been focusing on big data, right? On the other hand, for this company, there is no clear strategic focus area. It seems that the company has been running on diversified strategy. By the way, this company is one of the major multinational conglomerates. And using the patent data, we calculate the score, the firm level score, and then based on the score, we came up with a new index. It's called NASDaq Global Disruptive Technology Benchmarking Index. And this is second example, product review data. It seems like very boring, right? It looks very boring. And this is the box plot of, time series box plot of product score. And most people, most people just give product review score between 4.5 and 5, and some people give 5 or 1, which are extreme outlier. So if we remove the extreme outliers, this plot will become much more boring. But if you take a look at the same data from different angle, you will get very valuable insight. So the time series on top is volume of product review and the number of product review in a week. And quite messy time series plot at the bottom is the all financial items in financial statement. So we thought that the volume of product review could represent the number of products sold, which is related to operating income and revenue. So that if there is lead and lag relationship between the signal, I'm going to call the time series plot on top as a signal. If there is lead and lag relationship between signal and any of time series on the bottom, we could use the signal as a proxy for fundamental. And to figure that out, we decided to use dynamic time warping distance measure, because that measure uses elastic nonlinear alignment so that it can measure the similarity between two time series in different length, ignoring the time shift, which is not possible for the Euclidean distance on the left. So how dynamic time warping works? We have a signal with the length of n and signal r with the length of m. In order to compare the two time series, we need local distance, right? And in order to compare each pair of every element of sequence S and R, we need distance matrix. And the goal is to find out the best warping path, having minimal overall cost, distortion, or distance. And usually, the best warping path runs along a value of low cost intuitively. And you may notice that the number of possible warping paths is increasing exponentially. So we should set some constraints to reduce the search space. And one of the constraints is boundary condition. So every warping path should start at 1 and should end at the last element of the sequence. And the second constraint would be, second constraint is the warping path does not go back in time index. And there are more constraints, but I'm not gonna cover all of those. So once we identify the warping path, all warping paths for every possible combination of sequence SNR, we do time series clustering on the distance matrix. Especially for this project, we use conglomerate complete link array of hierarchical clustering, because that algorithm leads to tighter cluster, and it is based on the similarity, minimum similarity of pairs, right? So it starts with every data points being in its own cluster, and it joins two clusters that are the most similar. And this process is repeating until there is only one cluster. In other words, all data points until all data points belong to the same cluster, right? So this is the dendrogram from the time series clustering. And this is a plot of all time series used for the time series clustering. It looks quite messy, but if you plot one of the cluster that contains signal, you will notice that the time series clustering is well performed, well clustered, and the signal can be a proxy for cache at end of period and cache during the period. So far, I've covered just 2 different data sets, but hope you got a sense of how useful the alternative data sets are. And so by using the platinum needle, you can do whatever you want. So you can make shoes, you can make jacket, or you can make sofa. And yeah, and I will pass the microphone to Doug.
Thanks, Shinsu. All right, so I'm Doug Hamilton. I work on some reinforcement learning stuff with NASDAQ's Machine Intelligence Lab. I'd like to thank Hinsu for presenting, because while I get to do the fun, sexy work of talking about the Holy Grail, which is algorithmic trading with machine learning, searching for the Holy Grail without doing good data engineering and vetting first will lead you to a lot of bunnies with sharp, nasty, pointy teeth. And yeah, Monty Python references always slay at tech conferences. So, thank you. No, it's very important stuff. So we're going to talk a little about why it's important, again, to reach out across all of these various alternative data sources, and how and why we apply a reinforcement framework in order to extract some meaningful signal. So let's go to the next slide. So let's start off by talking about why we care about alternative data sets. So what I'd like to do is actually, these are real features from one of the data sets we host: overbought, oversold, weekly momentum, daily momentum. These are important measures in technical analysis, of the actual technical analysis kind, not the weird charts that you see on CNN Money. But these basically measure things about, are rough proxies for how momentum-like the market is. If it's gone up yesterday, how likely is it to go up tomorrow? And overbought, oversold is for the opposite, which is mean regression, reversion type markets. So how likely it is to go down tomorrow if it went up today. So let's go back a little bit. So what we like to imagine when we get a data set that's been curated for us is that we get nice orthogonal vector bases like this along each feature. But what we actually find, now we can go to the slide, is that it looks a great deal more like this, right? We have lots and lots of vector bases, but they're all highly correlated with each other. And we learn a lot about our E1 basis maybe we can kind of tell you something about the E2, but E3 is alien, right? We don't have anything coplanar with that, which sucks because it means that it seems like we have lots of information about the world. We actually have very, very little, right? If we want to think about it more tactically or tacitly, I guess, if I gave you a data set that had the following three pieces of information in it: the population of the United States, the number of men in the United States, and the number of women in the United States, which turns out the population of the United States is very important for predicting GDP, you'd probably tell you I didn't provide a whole lot of information outside of, population information. I'd say, but I provide you these other two columns. You'd say, but they're proxies for the other one. You're a dumbass. Shut up. So yeah, this is what we actually see when we look at curated data sets. It turns out that if you know the name of a ship, you know where it's going, you know where it's coming from, you know what it's carrying. If you know something about weekly momentum, you know a lot about monthly momentum, you know a lot about daily momentum, which is probably not so surprising when you say it out loud, but when you actually look at the intercorrelations between these things, it's a little disappointing. So what would we want to do? Let's go to the next slide. So what we might want to do instead is reach out across these alternative data sets, apply one of our favorite filtering mechanisms. I like MR, maximally relevant, minimally redundant, or we have an internally derived one called Galois that's really cool, to find these orthogonal vector bases. So in this case, we might keep our overbought, oversold, we might go grab Federal Reserve sentiment, and we might also get the inches of rain in Toledo last week. And that's a lot more orthogonal, right, than our previous case where everything was basically just telling us whether or not lots of people had bought things yesterday and we're still feeling good about the world. And with that, we can kind of reconstruct metrics like daily range because they're coplanar with these if we want to or if we have good enough information. Slide. So hopefully I've convinced you that getting lots of alternative data is important. And we'll talk a little bit about a couple toy problems now where we'll use some alternative data or lots of different. So let's say you're trying to categorize or curate a playlist for somebody using machine learning. You might go out and get a whole bunch of data on musical genomes, so what instruments are involved, what genres, et cetera. You might use your internal data about users and what they listen to and be able to do some collaborative filtering, or you might just throw the kitchen sink at it and use music charts, all music reviews, and of course the weather in Trondheim, which is really important for certain genres. Similar toy problem. Say we have a release for some software. I'm sure we've all been there, and we are in pre-alpha, and we're trying to make decisions about whether we should move to alpha, went from alpha to beta, and from beta to full launch, and eventually make money, which is our goal. And to do that, we have resources, we have engineers, we have marketers, et cetera. We have servers, we have computers, we have donuts and beer. And we also generate lots of bugs and reviews. Sometimes those reviews are reviews that in industry rags, sometimes those reviews are internal. And all this lives in the context of our overall financial health. And the question is, what should we do? How should we move forward? And again, when we talk about all these, we've mentioned a lot of types of alternative data. We have our internal books, we have the resources we have under control, we have the current state of things, what state are we in, and we have the bugs and reviews that we've seen. So lots of different data that we can put in, produce analytics on this, and try to help us make a decision. Slide. Cool, so hopefully I've convinced you that indeed we want to go out and get lots of different types of data so we have a wide view of the world. And I know what you're thinking now. We have a wide view of the world. We can see things clearly. All we need to do is make sense of it. And I know how to build a classifier. And if I can see things clearly and build a classifier, I can figure out when stocks are going to go up and when they're going to go down. So that's what you do, right? So first of all, side note, how amazing is it to start giving these talks about 3 years ago? And if 3 years ago, talking about a neural network would have been basically the big thing, right? And here's like, who cares? So you build your network, you go to your up-down classification, you let it train, it performs brilliantly. You get 56% accuracy, which in our world is really, really high. To be right 6% more often than you're wrong. You get to 56% accuracy. Life is beautiful. You're able to figure out when things are going to go up and when they're going to go down. And you take your paycheck and you're going to go implement it because what could go wrong? Well, everything. Because it turns out that you're basically at the mercy of return symmetry at that point. So fun facts about returns. Return symmetry. One, it's not symmetric. So if times are good, you're going to do better. If times are bad, you're going to get crushed. And the good people at JP Morgan will take your donation kindly. Other bad news, because it gets worse. It gets much worse. It tends to be negatively biased, right? So that sucks. Let's go. We can go back. Also, Kashi. Kashi distributed, not normal really. So the tails are going to annihilate you as well. So you can do that. You can classify, and you can get your up downs, and you can bet on them. But they don't tell you anything about how to manage your portfolio. They don't tell you anything about the value of not investing in something. Because when you choose to invest in something, it means you're also choosing to not invest in something else. It's a really complicated dynamic control problem, this portfolio management problem. So let's go to the next slide. So what do you do now? Well, you can curl up into a corner and cry. Now this works in other industries, because when you curl up into the corner and cry, you also guzzy up your resume and apply to a bank. Problem is, you can't really do that here. You're already there, you're stuck, life sucks. Second thing you can do, because oftentimes if we have this problem, what we might think about doing is having a simulation, wrapping an optimizer around it, and when we do that, we end up with a way to adjust our input parameters, adjust our control elements here, the amount of things that we're buying and what, to get an optimal result. And we might be able to learn something about how to generate rules that can produce good returns going forward. There's a lot of problems there too, which is that we have to have some notion of how to simulate a market, which is hard. There's not a lot of good physics going on. We also then have to figure out how to do an optimizer in the future for things that happened in the past and also make money on it, which is also hard unless you have a time machine, in which case you should go bet on the Cubs winning the World Series. So what's the last thing you can do? And this is something I'm sure we've all done at some point, which is say, well, I've got a regressor or a classifier that's kind of working pretty well, 56%. I can interpret that as a signal, a buy and sell. Then all I have to do is figure out some decision layer to put over that signal, and I can measure a result. Because that's where the problem is, right? I just need to interpret my ones and zeros, my ups and downs, a little bit better. And then I'll get a result. This is a really good insight, right? And we see this actually a lot with machine learning that's deployed now, is we do some interpolation, some heuristic, and we're good. Slide. So problems there too, because life is misery and pain. So you build your regressor, your classifier, and that's great. You pass it through you interpret it as a signal, you have a decision interpretation, you have a measured result. Every step along the way, you add error. And because this is the worst of all possible worlds, error always works against you. It doesn't work for you. And everybody on Wall Street is just waiting to rip your face off if you have any errors in your model. And the only place that learning is occurring is in your regressor or classifier. Nowhere else down the chain. Repeat that. The only place where learning is occurring is in your regressor or classifier. So you have a beautiful regressor or classifier, and then you add errors by making decisions on top of it. And that sucks. It's a horrible thing to do. If only there was a solution. Maybe there is. End-to-end approach where we can take all these disparate elements, encode them into one beautiful model, and we end up with an end-to-end solution that makes the decisions for us. I'm going to repeat that again. That makes the decisions for us so that we don't have to use our stupid meat brains to make decisions because we're bad at it, especially in the context of trading and financial markets. Slide. Okay, cool. I once read a book that said you're only allowed to use one equation per presentation. It was by a string theorist. So he suggested that the equation used is E equals mc squared, and then proceeded to present like a Boltzmann heat diffusion equation, which is considerably more complicated. I'm taking that to heart, and I'm going to give you the value state Bellman equation, which is big and nasty looking. The value state Bellman equation is the key principle behind reinforcement learning. And where our loss in classification is typically derived from something like cross-entropy loss, here what we're saying is that the value of taking a particular action under a policy, so policies generate actions given a state, is equal to the expected reward we get from taking that policy now, plus the expected reward of all potential future action state pairs, which actually kind of makes a lot of sense, right? It's a network that grows really quickly, makes a great deal of sense. So important thing is that pi there, that's our policy, again. And if we look at this equation and think about the policy evolution that occurs here, what we really end up with is the picture right below, where we have a policy, we evaluate that policy, we make a change to that policy, and we reevaluate it. That's a lot easier. And that's essentially the, that's the general improvement loop that defines reinforcement learning. Is we create a value, we create expected values with the equation above, and then we iterate on it in the diagram below. So that's reinforcement learning in a nutshell. There's lots and lots of good resources that you can learn more about it. But essentially the notion here is that we are able to get rid of this notion of classifying and regression as our means to an end, and instead have actions that we can take. And actions are good because that's what we want to do, and we don't have to do any more abstraction, which introduces error. So reinforcement learning 101. In machine learning, we learn from examples. In reinforcement learning, we play a game. Epochs and batches kind of become episodes. Losses are rewards. Classes are actions. Optimization is that policy iteration. And then convergence is a really nice word, policy optimality. So this is kind of the framework we have now for thinking about reinforcement learning going forward. So let's go back to our toy problem. Let's say because you're not a whimper poser, you want to rock out to some Man of War on your favorite music app of choice. And so what they do, they see that you like Man of War, they push it through their genome, their music genome, they push it through their classification, their kitchen sink, then they apply some clustering and they say you'll also like this, and it's terrible. It's great at first, but then you find out that they basically play the same 20 things over and over and over again. Has anybody had this experience? And maybe you think, well, if I like something, it'll get better, but it actually gets worse because it overreacts to it. And the only thing worse than liking something is disliking it, because whatever idiosyncrasy exists that made you dislike it is not the reason they thought you disliked it. So now your station's all messed up, and you have to uninstall the damn thing and start again. So how can we reimagine this as a reinforcement problem? That would probably be better, allow us to actually explore a space continuously and continue to have better and better performance for a customer or for a user in the curation space. So here's some ways. You know what I like when I listen to music? Not skipping songs, especially if you're in the gym. So we could have an action which is, what next song should we play? And our episode is you play until somebody skips a song, you get 1 point for each song skipped. So this is how we iterate our policy, right? When somebody skips a song, the episode ends. So our goal is to have to build a model that can produce really long strings of consecutively played songs. Alternatively, we might want to maximize the liked songs before exiting a station. So this is one that would probably end up resulting in a little more exploration because you can't like a song twice. Again, one station use would be our episodes here, and our policy and the reward we get is +1 for each like, -1 for each unlike. And the policy iteration is we have a policy, we want to see how many likes we get in a loop, and then when we see how that we make small changes to it, we see how we do next time. If we do a little worse, we go back. If we do a little better, we keep going down that path. We play with things like how often are we going to introduce new songs or play the same one again. Is this person that wants to really focus on one thing or wants a lot of preference or a lot of breadth in choice? So that's another way we could play this game. Finally, how can we play this game? Maximize unskipped songs before exiting a station, which is a little different from consecutive songs until unskipped, because you're allowed to skip without exiting the station. So again, one station use, +1 for each song, -1 for each skip, -2 for each unlike. Right? This is going to produce a slightly different model that takes slightly different actions, takes slightly different risks in what it presents you, and also takes slightly different risks in what it thinks is important about the song that it chooses. So for example, in this one, it might choose really, really short songs because it wants to push the most through at once. So it might have a preference there. So these are all ways we can take what was a clustering problem or a classification problem and reimagine it as a reinforcement problem for playlist categorization or playlist curation. Slide. Cool. So now we're going to actually talk about what we did with reinforcement learning in practice. Now we've gone through our toy problems. So again, we'll take the 3 data sets that Hinsoo talked about earlier, our patent application data, our salary data, or our HR data, and our product review data. And we construct here what I think you'd all agree looks like a reasonably orthogonal set of vector bases. We also did this in a more formal way, internally, obviously. So we did this. We construct a nice orthogonal set of vector bases for it. From these, so number of ML patents, from patent applications, open recs, processing time, that is how long does a rec stay open, in our HR data, and number of 2-star product reviews from our product review data for companies. So then what did we do? Well, we did the first thing everybody tried to do here, XGBoost classifier, up-down movement, up is long, Long here means we're going to bet on the stock going up. We're going to buy it, basically. Down is short. Short means we're going to borrow money now and pay you back with stock later. So we're betting on it going down. How do we perform? Really, 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 really bad. Cautionary, please don't do this at home. So bad. Coin flipping did better than us. We lost money in a time period when the S&P 500 grew by 40%. The stocks we were trading were the S&P 500. Okay, so is anybody going to go home and try to build an up-down classifier and trade on it? No, good, okay. So the next thing we did is we built a classifier. Again, we say, let's apply some heuristics. We hire some folks out of MIT's MFIN program. They're reasonably bright. Maybe we'll let them give us some heuristics about how we should trade on these things and maybe where our uncertainty principles should be here. Maybe we should just ignore some stocks if we don't know enough about them. So same thing, classifier, up-down prediction, and we'll have a threshold where we'll just ignore it. So good news, we didn't lose all of our money. The bad news is we performed at 75% of the benchmark, also undesirable. Because performing at 75% of the benchmark means we would have been better off just popping the money onto an index, walking away and not fretting about the whole thing, living our lives, getting coffee and eating donuts. The last thing we did was probably the most sophisticated before we threw in the towel on these approaches, which was built a regressor. So our regressor is going to predict price vector well, which is hard and another thing you shouldn't try to do if you want to get sleep at night. And then we built on top of it something called a parametric allocation model. Effectively, we're able to use our expectations about how error is distributed across regressive models to help us figure out how to allocate our money between stocks. So success, great news. In our holdout set, we outperformed our benchmark, the S&P 500, by about 10%. So that's actually pretty good, right? Not 10% in that the S&P returned 7, we got 17. 10% in that the S&P got 7, we got 7.7. Now, that's pretty good. The problem is that you end up trading a lot because every day, not only do you change the bundle of stocks you're holding, you're also changing the amount of each stock you're holding, and nobody lets you trade for free unless you're a market maker, and nobody in the room here is a market maker. So the last thing we tried was, partially because I got told if it doesn't work better, it's over, was a reinforcement learning scheme. So what we implement here is deep direct policy gradients. It's a 1998 paper. That's actually, I think it was 98 was the deep direct, well, policy gradients is 98. Deep direct might be sooner, more recent. So we apply deep direct policy gradients. We train it up. And what's amazing here is that we go from that 110% threshold to 135% of the benchmark. So that means we go from a 10% return baseline, 11% return with our fancy parametric allocation, and then to 13.5% with our reinforcement learning scheme. And what a reinforcement learning scheme learns, which is really cool, is not just about up and down, but it learns not to buy things that just go up a little bit. In fact, it learns to not buy most things that just go up a little bit. And it gets pretty good at only buying things that go up a lot. It also gets pretty good because most of the time when we're talking about returns in finance, we don't actually care just about the returns. We also care about limiting variability. It also learns to buy things that work against each other and give us a slightly flatter set of returns as well. So that's pretty cool. And essentially, that's our approach to reinforcement. That's our foray into reinforcement learning. And I think a really interesting test case for its use in a broader context, even outside of financial markets. If you can reimagine a game to go from, or reimagine a case to go from a classification game or a regression game and into one of these action decision games, then you can remove a lot of human decision making from the process that's either baked in the code and probably wrong in some very subtle way, or that is explicitly made by your boss or manager. And I know we all love our boss and manager, but they can be wrong too. Occasionally they don't read data correctly. And really automate these processes and end up with much, much better results. I think that's the last slide, right? Thank you. Yeah. So I guess with that, we'll take some questions.
We got time for Q&A. Anyone have any questions?
Hi.
So is there any hope of learning enough about the dynamics of the system that you can do reinforcement learning and simulation and not have to risk real money and so on and so forth?
Oh man, I don't know what the politically correct answer is to this. There's probably an answer that doesn't involve saying not if you're only if you're not a coward. So yeah, I mean, there's not enough that you can. I mean, can you learn enough about the dynamics without risking real money? That's tough. So one of the things that makes financial markets really difficult, as opposed, right? Like there's lots of things that are difficult about image recognition and voice processing, but in a lot of ways, you know, image recognition, particularly facial recognition, it's Markovian, it's fully observable, stationary. You know, people's faces don't change that much beyond a particular set of distributions. Financial markets aren't. They're evolutionary systems, which makes it really, really difficult. Any model you build is invariably going to be wrong sooner or later. So the question is, hopefully it's later. Hopefully it's wrong in such a way that you can catch that it's wrong. That's a whole nother bag of worms of what do you do when your model starts going wrong. Can you do it without risking money? Sure. You can paper trade and see how it runs in real time after you paper trade. But typically what you'll do is you'll run a back test on your int sample, and that's how you kind of figure out if your model's working at all. That's where we'll get our rewards for our reinforcement learner. Our holdout, then we'll backtest as well. So backtest basically means we pretend we trade on it. And then the last thing we do is we paper trade for like, you know, mega holdout or whatever you want to call it. And I guess you could claim that that's kind of like learning the dynamics without risking money. If you tell anybody at Acadia that, they'll laugh you out the room though. So, sorry.
About the parametric allocation model, so are you saying that you sort of recombine the decisions based on their expected error pattern?
Basically, so I mean, there's certain things that we know about regressive models, about how, or we have expectations at least, let's put it that way. We have expectations about how error is distributed around regressive models. And one of the nice things is that baked into the way we build generalized linear models is that error is normally distributed around the prediction. So we can, and I believe it's, I'll have to check my notes, but I think it's that the RMSE is basically equal to 1 standard deviation. So we can use that to kind of assess how certain we are about a certain uppedness versus a certain downedness. And obviously in this case, what we're doing is we're allocating more into the more upped stuff and less into the things closer to 0. And that's both on the long and short side. Now, of course, in reality, a lot of those assumptions about the heteroscedasticity of that error distribution isn't true, nor the normalcy of its distribution about the mean going forward.
And just one quick one. Did you say Galois?
Yes, that's the name of our internal method or internal tool that helps us with the feature selection process.
So are you using abstract algebra in your work?
It's none of your business. No, but we do spend a lot of time talking about French Revolution. Yeah.
Is one of your alternative data sets tweets? Maybe from
one of our alternative data sets is tweet-based.
This is from an old guy. Has Warren Buffett used any of these models?
God, we don't have enough time here to talk about Warren Buffett. But if you look at Warren Buffett's investment portfolio, he had a really good decade. And ever since then, his life has been a testament to just boring 7% returns per year. But he had a really good decade. Yeah. And then he's been just doubling every 10 years since.
Hi, you said that one of the trading data sets that you were working against had a 40% return over, was it a short period of time, or was it sort of a typical set of returns?
Return. Oh, so that's, the S&P 500 had a really good run. So buy and hold, a strategy of buy and hold, which basically means I bought the S&P 500 on Saturday. I waited a year, well, I waited on Monday, I guess. I waited a year till the next Monday, and I had 40% more money. So that's what I was talking about.
It just seems like that might be not the optimal trading data set to use or to compare.
Yeah. So one of the
Fairly
challenges
atypical.
that Hinsu alluded to actually with alternative data is exactly that. Typically, when we talk about using data in trading engines, we want a lot because we want to see lots and lots of different market conditions. But I think one thing that we've both been reminded about working in this space is 5 years ago, most people didn't have smartphones, right? 10 years ago, there was no Twitter, something like that, or if there was, it wasn't anything that we were part of. Facebook was private 10 years ago? Facebook was private 10 years ago, right? Yeah, it definitely was, because it went public in 2011. I remember where I was that day. Yeah, so a lot of this data simply didn't exist that long ago. So when we look at the alternative data that we have, it basically runs the gambit of a very long and robust bull market. So what do you do about that? Well, do you think the market's going to crash soon? If you do, then maybe you shouldn't be using alternative data until it does. If you think we're going to be okay for a little while longer, then you can roll the dice. It's up to you. None of this is financial advice. Okay. Yes.
Thanks. Great presentation. So I have a question. It's about the recommendation that you give, and I was curious as to if there is a parameter that you can add in the reinforcement learning Bellman equation which adjusts how risk averse you are.
Oh, absolutely. Can we go back to that slide? Sure. So the value state Bellman equation is almost as beautiful as the state value Bellman equation, or is it the state action Bellman equation? But they're both quite lovely. So the answer is yeah. So one thing you can do is you'll see this gamma parameter here. So you can adjust this gamma parameter. So the gamma parameter tells you about basically how far forward in the future you want to look. So the smaller that number is in a certain sense, the less time risk you're willing to take. And then as far as the other things within the Bellman equation, that's probably the only thing you adjust there. Aside from that, what you'd probably do is adjust your reward calculation. So, pretty typical reward, one that we use was Sharpe ratio, which is returns divided by daily return, or average daily return divided by variation, that average daily return. There's no reason why it has to be 1 times the variation in daily return. You can make that higher. If you want to be even more risk averse, you can use things like, what is it, the one that only cares about downside risk? Bill, what is the one that only cares about downside risk? Sortino rate. You can use metrics like Sortino ratio. Thank you, Bill. That'll only care about your downside risk and make you a little more risk averse. Basically, what Sortino ratio is telling you is that you're not clever for getting outside returns on the upside. You're only condemned for getting them on the downside of your distribution.
So a different question back on the orthogonality charts that you had early on. Even though things can be strongly correlated, sometimes those small eigenvalues going in that orthogonal direction can actually have a lot of classification performance. So when you're going through this process, how do you determine, if you think it's something that's more useful than adding something that's orthogonal, but is the weather time?
So that's a really good question, and I mean there's a lot of different frameworks for doing this. I'll introduce 2 generalized ones. One is a wrapper method, and the other we'll call a theoretic method. So I think the one I introduced earlier was MRMR, which is an information theoretic approach. And this is really looking to get things that are as orthogonal as possible while also being correlated with a target. So that kind of starts to tackle that problem. The second is wrapper methods, and a classic wrapper method is we're going to build a classifier. I know I said don't build a classifier for this problem. We're going to build a classifier this one time for this problem. And what we're going to do is we're going to find sets or permutations of features that give us really good classification performance and claim that those are good, and we don't necessarily care so much about the orthogonality. And of course, we do something in between as well.
Anyone else? Oh, lots of repeat customers.
So do I just turn on my system with random policy and do policy iteration in the real world, or do you somehow compute some initial policy to start with?
So you could, but you kind of start randomly. There's no reason not to, provided that you're not putting money behind it initially.
I'm losing money if I have a
right. So you're not going to put money behind it initially. Remember how we talked about that back testing. So one of the challenges, if you're bigger than, let's say, I'm just going to make an assumption, you're not moving $1 billion on E-Trade every day. Is that true?
Maybe.
Okay. Provided you're not moving $1 billion on E-Trade every day, the market doesn't really care so much how you act. I mean, it responds a little bit. If you ever took like an intermediate macroeconomics class, you probably remember the large and small country theory.
So paper trading is going to be very close to the real world.
Yeah,
dynamics.
right. Because at least historically, because you're not, the 100 shares you bought this morning don't have that big of an impact on the world when other people are moving 10,000 every second. Yeah. Now, there's really interesting ramifications if you think it will, but maybe we can talk about that later. There's some interesting notions in reinforcement learning around GAN and loop reinforcement, but that's for different.